we stopped here yesterday on the MDS. So I think I'm actually gonna go back in there to, re-explain that. Of course, the MDS actually means multi-dimensional scale. We're looking for a way to reduce the dimensionality in a data set in such a way that the original distance in the high dimensional space will actually be preserved, after, projecting that into low dimensional space. And if we want to see the way it works algebraically, it means I actually need to figure out some coordinate, which will indicate the position in the low dimensional space. And that very coordinate is what we call Z. Okay, this guy here, Z. Okay, and the question is, how do we derive Z? Because Z are the coordinates in a lower dimensional space. So how do we derive that? What I'm actually projecting now will show us algebraic step to do that. So if I want to do that, the very first thing I need to do is to obtain, derive B. And how am I going to get B? Okay, I need, if you take a look at this guy, that is the similarity. The similarity. Now, if I have that guy, I will be able to obtain a matrix A. Okay, and the moment I obtain a matrix A, and if you take a look at this guy, that H is centering, which is identity minus identity multiplied by identity transpose divided by n. This is more or less like I'm centering. Okay, now if I know my H, if I know my data, I will be able to get A. And the moment I get A, I will be able to get B. Okay, you can see B is H multiplied by AH. And after getting my B, then I will apply my knowledge of agent decomposition. Okay, so when I have agent decomposition of B, it's going to lead us to that. The agent decomposition of B will lead us to that. And the moment we have that, that is the same thing as this. Don't forget, what do we need? We need a Z. That very Z that we need, they are coordinates that represent the position of data in a lower dimensional space. So this explains the algebraic derivation of that. Okay? Now, I said, however, such a position we usually give a Z as an n-dimensional, and we may specifically want a lower dimension D. Okay? And the solution to that is we're actually going to apply our knowledge of eigenvalues in the singular value decomposition, where we're not going to use all the eigenvalues. We're only going to settle with maybe the largest one. Okay, don't forget, we are not interested in perfect information. Why are we not interested in perfect information? In the case of, we're talking about image, the perfect information is when you use all the singular values. Don't forget, we have issue with space, and we're trying to reduce in such a way. The essence of that is just to reduce the dimension so that we save space. Okay, so we're going to use the same idea here. Now, I needed to pay attention to this guy. I said the first D columns of Z. Let me tell you this. If you look at Z, it has from Z1 to Zn. We don't want to use all of them. We only want to settle for the lower dimension. That was why I said the first D columns of Z corresponding to the largest eigenvalue will give the best D-dimensional representation of data. Now, when I say the best dimensional representation of that, don't forget this guy is the original dissimilarity. The dissimilarity in the original data set. and the original data set is of I dimensional, can we have a way to represent the dissimilarity, okay, in the I dimensional data set in a lower dimensional data set? That is the idea, okay? And that is the reason why we're interested in that. Now, and that was why I said this is very similar to PCA, where we only make use of a low rank representation. The low rank representation, okay, it means we're using, if the matrix has a full rank, we're not going to use the full rank. Using the full rank means you are using all the singular values. We're not interested in that. We actually want to reduce some maybe less important features in such a way that at the end of the day, we're still going to, retain the most information. And that's why, this MDS is more or less looking like a principal component analysis. Now, I needed to pay attention to this guy. I said, if the given dissimilarity are true Euclidean distances in the original space S, then I can say the classical scaling is equivalent to PCA. So what am I trying to say here? We have a dissimilarity in the original data set. And after reducing the dimension of data set, do we still preserve the distance? That's what we mean. Does that make sense? Okay. Now, and because of that, to be able to know whether we're going to preserve the distance, let me tell you this. You cannot eat your cake and have it. There is no way the distance in the lower dimensional space will be exactly the same as the distance in the higher dimensional space. There's going to be a gap. And how am I going to know if the number of dimensions that I've chosen will retain the largest information or will preserve what the distance that was observed in the original data in the lower dimensional space? Then we need a metric of evaluation. In the metric of evaluation, there's going to be a loss function. Why do we have a loss function? Because there's an acknowledgement that we're always going to be a gap. That's what we call loss function. Then we want to minimize that gap. And that is why this is going to be a minimization problem. Take a look at that. We want to minimize a loss function. We know something is going to be lost. That's no problem. But how can we minimize it? Okay. And that's exactly what you see right now. Okay. I said in general, the similarity may not correspond to Euclidean distances. You have a dissimilarity, like the distance between data point in the high dimensional space. And you also have distances in the lower dimensional space. Now the question is the distance in the higher dimensional space preserved in the lower dimensional space? If I'm going to answer that question, there's not going to be exactly. There's going to be a gap. We'll try to minimize the gap. Okay? Now, I need you to pay attention now. We have different kind of loss functions that we can use. Okay? Of course, in statistical analysis, you hear about sum of square error. Oh, we want to minimize sum of square error. And you heard about absolute, error. The error can be in two ways. Either I'm looking at the absolute one or I'm looking at the square one. There's something that I call a square error loss, an absolute error loss. Also in multidimensional scale, okay, of course, we have different kinds of, that can be used. So when I talk about loss function now, number one, I needed to pay attention to this guy. Take a look at this. That guy is the distance, is a similarity, the distance in the original, the between points in the original data structure, in the I-dimensional. But what about this guy? Give me 1 second. This guy, you can see that this guy, the DIG has to do with Z. What is the Z? The Z is a coordinate that tells us the position of data in the lower dimensional space. So there are two forms of a distance. The very first one is this one, is the dissimilarity between data points in the higher dimensional space. The second one is another distance, which is the distance between point in the low dimensional space. Does that make sense? Now what are you trying to do? You're trying to look at the sum of square distance. Okay? Now, but if you take a look at the second one, if you take a look at this, you're going to see that this one is squaring each of these. It's squaring each of that, right? Look at that. Is it not that? Why is it squaring it? Because the second one that we call the least square is trying to reduce the influence of small changes. Because at times small changes may not that, and because if you take a look at the first one, the least square on distance does not square each of the distance. But right now, this guy is squaring that. And the reason why he squared each of that is just, to reduce the influence of small fluctuations. But let's take a look at the third one that we call the least square on inner products. This will happen. This one here is actually going to consider the difference between the inner product in the dissimilarity matrix and the inner product in the lower dimensional space. And not only that, it did that by centering. If you take a look at H is part of this. And that's why the third one is a very common loss function used in MDS. Does that make sense? So these three are the, the household name stress loss function use. If I really want to see whether the MDS is doing a great job. Okay. But I said the third one is actually very, very common. Now, let's go to the comment right now. Now, comment on loss function. I said, wait for individual similarity can be incorporated. Okay. I talk about individual similarity as a weight. Okay. Then I said, normalizing the stress function made them invariant. Okay. To rescaling of the similarity. So we do normalization. We do centering. Okay, that was why I said the third one the other time. Make a whole lot of sense. And I said SS stress is similar to S stress. I said, but give more emphasis to larger distance. I'm talking about this guy. I'm talking about this one here. That one that we squared before. I said it's similar to this, except that this one here actually emphasizes on large distance. When you square something, it's going to be large, right? Okay, so that is what that statement is talking about. And I said strain, which is the third one, give nested solution. The first two dimensions of a three dimension are the same as the two-dimension solution. So, I told you the third one, the loss function, is very, very crucial. It's the one that we use, let me just say, most of the time when it comes to evaluating the loss function in the MDS. Okay, choosing dimensionality. You remember in PCA, in principal component analysis, we also face with identify the number of pieces, right? The numbers of pieces that is playing the maximum. At times we choose the first two, the first three, and so on like that. we're also going to be faced with the same challenge here in the MDS. How do I know the numbers of dimension that work? When I say the number of dimension that work, what am I talking about? What I'm talking about is how do I know the numbers of dimensions to arrive at in order for me to preserve the distance among the data points in the original high dimensional space in the lower dimensional space. It is not all dimensions that work. We want to identify the dimension that is going to work. Does that make sense? And we're going to have this formula here. Let me tell you this. This formula here is very close to variance explanation in PCA, but I'm going to tell you the difference, and I need you to pay attention. You know, in PCA, in principal component analysis, if I really want to know the contribution of a particular principal component, the first one has the largest contribution, right, in terms of variance. If I want to know the contribution of that one, I'm going to write the contribution of a particular principal component divided by the totality, right? That's what we do in PCA. But do you know what we do here? What we do here, the numerator is not explained, but the numerator here is unexplained. It's like unexplained over the total. Does that make sense? No, so when I have unexplained over the total, okay, now if this particular formula is large, that's not good. Because don't forget the ratio, what you have in the numerator is unexplained. And what is unexplained? You see the distance, right? The distance is unexplained. In statistical analysis, when you look at predicted minus actual, okay, predicted minus actual, okay, is error, isn't it? What is the error? Error is unexplained variation. Now here, we're talking about the percentage unexplained to the total, okay? Now, when you look at the percentage unexplained right now, if the answer that you got is very large, then that's not good, which means there's a very huge loss of information. Does that make sense? Now, and you know what? We can plot that, okay, and see. But when we are plotting, we're going to plot this against dimensions. You know what we did in clustering? You know what we did in clustering the other time, where we use able? In that one, what we have in the denominator was actually number of clusters, right? But this time around, it's actually stress in the vertical axis against the dimension, numbers of dimensions. But there's a rule of thumb, and I want you to see the rule of thumb. I'm going to start with this. The rule of thumb given by Kruska. Take a look at this. You know what I mean? If this guy equal to 0, oh, we're going to be celebrating because it's unexplained variance. And that's going to be a perfect, but I don't think that is going to happen. Because the reason why that is not going to happen is because when you project, something into a lower dimension, the distance in the original, the dissimilarity among the data point in the higher dimensional is never going to be the same when you use a lower dimension. Does that make sense? And that's why you are not necessarily going to have 0% as a stress. When it is 2.5, that's an excellent. When it is 5%, that's good. When it's 10%, that's fair. But when it is 20%, that is poor. Oh, 20% poor. You remember in principal component analysis, if you want to choose the number of principal components, they will say at least 80 cumulative. Yes, so, and don't forget, this one is like going inverse, like, because in the principal component, we're talking about the percentage of variation explained. But here, we're talking about the percentage of variation unexplained. Does that make sense? Okay. Now, we're done with the MDS. Now, MDS is only useful when we're actually talking about linear. You remember PCA PC and MDS work on linear. Don't forget the principal component is a linear combination of the original features. The same with MDS. But the situation, and that was why I said if data are on a curved subspace, then the Euclidean distance is no longer appropriate. Euclidean distance is applicable for linear. Does that make sense? For non-linear now, okay, we cannot compute Euclidean distance. And you know what? In MDS, Euclidean distance is what we use to, to compute the matrix of inputs. But what are we going to use? Instead, we're actually going to talk about ISO map. Okay, so I'm presenting you, I'm introducing you to ISO map right now. ISO map actually is a non-linear version of MDS. Does that make sense? ISO map is a non-linear version of MDS. Okay, and if you take a look at, a curve structure like that, you see that? So, but how does it operate? You know the way it operates? We're still going to apply MDS, but that will be at the later stage. Okay. Now, the very first thing we do, we identify neighbors, nearest neighbors. Okay. And how are we going to identify nearest neighbors? There's a particular approach that we use that we call, has anybody heard about KN neighbors? Okay. We use that to identify neighbors, the nearest neighbors. Okay. Now, we actually compute the Euclidean distance between the nearest neighbors. And after doing that, there will be some that are neighbors that are not very close. Okay. We also need to identify that. And we consider the shortest paths, between non-neighbors. And we also going to use Euclidean distance for that. Now, after the first one, the second one, then we can now apply the MDS. So MDS is also applicable in ISO map. Okay, now we apply the MDS to the distance matrix. Then we say, does the strategy work? Yes. And that is similar to idea of a spectral clustering. You remember spectral clustering? Where we talk about the density-based clustering? Okay. Now, I'll quickly give you this. Take a look at this. If I have 2,000 images, and each of this image, okay, they have a pixel intensity 20 by 16. So 20 by 16 will be 320. That's a lot of dimension, right? And in this image, we have what we call a finger extension and wrist rotation that makes that to be a kind of a curve. Does that make sense? Now, do you know what I'm trying to do right now? I'm actually projecting that into two-dimensional space. But in the vertical axis, that's a finger extension. In the horizontal axis, that's a wrist rotation. Take a look at that. That's super cool, right? Okay. Now, this is another set of data. If this is the original data set of multi-dimensional, if you take a look at that, then we can actually apply the idea of MDS depending whether we have a linear structure or not. Okay, but I want to talk about this one. Take a look at this. If you take a look at this MDS, look, I need you to look at the vertical axis. The vertical axis is the fitted distances. The horizontal is the dissimilarity. Now, the horizontal is the dissimilarity in the original data set, like the distance in the original data set, the distance between points. Okay. Now, when you convert the high dimensional data set into low dimensional data set, you're actually going to have a fitted distance, right? Now, do you know what I'm trying to do here? This plot is just going to show me to see whether the fielded distances matches the original dissimilarity. What are we trying to say? We're trying to say, have we been able to maintain or preserve the distance in the between the data points in the high dimensional high dimensional space in the lower dimensional space? That exactly. If I have a diagonal line, you know the meaning of a diagonal line, like a diagonal line is going to be a perfect match. There is nothing like perfect match. Does that make sense? Now, what we're going to do is this. Please, I need you to pay attention now. When I'm talking about a match, I'm going to look at a match in two ways. Number one, if I have some points that have a huge gap, I remember the other time when I was talking about the distance between Warsaw in Poland and Madrid in Spain. You know, in the original data set, the distance is so huge, right? Now, if I now go into, after reducing the data set into two-dimensional, I also want to look at the distance. Is the distance still huge, even though they may not be exactly the same distance? Okay. Now, when I look at in the original data set, for those ones that are clustered, like Paris and London are very close, are they also very close in the low dimensional data set? Now, what this guy is trying to tell me right now, okay, for those ones that have a smaller distance in the high dimensional set, they are still able to preserve that in the low dimensional set. But for those ones that have huge distance in the high dimensional set, they were not able to preserve them in the low dimensional set, which means that is a loss of information we're talking about. Okay. These are forms of, you know, nonlinear beatings that we talk about. Okay, because of my time, I'm actually going to say MDS, a very useful visualization tool in many applications, and of course, you know, it makes us to visualize multidimensional data in a 2D or 3D, and of course, don't forget, there's always going to be a distance between the similarity and the distance in the lower dimensional space. And the only way we can actually see whether the distance is very small or not, if I want to evaluate that, we got metric of evaluation. I show you stress, SS stress, strain, and so on like that. And of course, I said the particular choice of loss function is often determined by